Okay, so last week we were talking, or the past 2 weeks maybe, we were talking about the connection between the poles of a system and its response. So in that regard, we started with first order systems. In that case, we have a single pole which is real, and that pole causes an exponential function in the response, and the location of the pole on the real axis determines how fast the exponential grows or decays. So the poles on the left-hand side leads to a response that converges to a constant number, and how fast it converges depends on where the pole is. So this converges slower, and since the pole is far from the origin, converges faster. And if you have a pole on the other side, then the response diverges, it goes to infinity. So it determines the stability of the system. Then we start talking about second order systems, starting with a special case of second order systems where the poles are purely imaginary. And in this case we saw that such systems tend to oscillate forever, whether it responds to an initial condition or responds to an external input. If you have a system with purely imaginary poles, then the response just grows, or doesn't grow, but it keeps oscillating forever. And we indicate there is such a relation that if the poles are closer to the origin, like this for example, then the frequency of the oscillations are smaller. Is it? Yes, that means the period of oscillations is large. But if the poles get farther away from the origin, then the frequency increases, which means you have more oscillations within a certain amount of time. Now, today I'm going to show you the most general case where we have arbitrary poles. So today's topic is so-called damped systems. So we're talking about poles that have both real and imaginary parts. Okay, so we're talking about poles like this. If you have a complex quantity pair, we have two poles and they are both complex numbers. So to represent a complex number, we need two scalar quantities, right? Its real part and its imaginary part. Two scalar quantities is required to express a complex number. Here we're talking about two complex numbers, but since the second one has to be the complex quantity of the first one, again, just two scalar quantities is sufficient. Okay, so if we know this pole, for example, then the second pole has to be the symmetric of the first pole. So there's no freedom anymore. So in other words, just knowing the location of one pole is sufficient to locate the other one. So if we know that the first pole is at minus A and plus B, then we know that the second pole has to be at minus A and minus B. So this means for damped systems, so let me just type it here. So we can express the locations of a complex conjugate pair of poles by using two scalar quantities. So in the case of real poles, one scalar quantity was required, and it was either the time constant or the location of the pole. If we have purely imaginary poles, again, one scalar quantity was sufficient, and that was the natural frequency, which was this distance. And now in the case of general second order systems, we need two scalar quantities. So these scalar quantities can be the Cartesian coordinates as shown here. Or we can use polar coordinates. Okay, and as you know, in polar coordinates, what we do is we specify the distance with respect to the origin and the angle it makes with reference axis. So this is our origin. In the polar coordinate case, we represent this length, and we call that length omega n, and we use this angle theta. Böyle gösteriyoruz yani, çünkü genelde solda köklerle uğraştığımız için stable sistemlerde. So the theta is measured with respect to the negative real axis. İstiyorsanız klimayı kapatalım ya. Ya bilmiyorum sınırsız da ben bayağı bir sıcak olmaya başladı burası. And in the second case where we use polar coordinates, okay, so if you want to express the location using polar coordinates, normally we can use omega and theta, but instead of theta we use cos theta, and it doesn't make a difference. So we use zeta. Harfleri yapması da çok güzel ya, güzel harflerini. Yun harflerini biz çok kullanıyoruz ya mühendislikte. Ve mesela şu şey beni hep zorlamıştır. Yani zeta bir de kısa diye bir şey var. Belki yeteri zor değilmiş gibi. O da biliyorsunuz iki tane kıvrım var. Yani zeta şöyle bir şey. Kısaydı bunda şurada iki tane var. Okay, so we use this zeta and omega n to express the poles. Okay? Now, let's see what these numbers mean on the response of the system. Okay, so let's start with the first case. Suppose we're using Cartesian coordinates. In this case, our poles are at minus a and plus minus bj. Okay, and here this a is a positive number, it's a positive scalar, and minus a means that the pole is on the left hand side. So in this case, let's see what the characteristic polynomial looks like. So we have one pole at, and then another pole at. So if you open the multiplication, you get s plus a squared, and then this multiplied with the real part here cancels this multiplied with the complex part here, so they just cancel each other out. And then we also have this multiplied with that, and that gives us minus b squared j squared, but j squared is minus 1, so that gives us plus b squared. Okay, so this is the characteristic polynomial. If the characteristic polynomial is in this form, then it gives us two poles at these locations. So that means we have the first part is something like that. There is some numerator, doesn't matter that is, and on the denominator we have this part. Okay, so the first part is something like that. And we know what the inverse of this looks like. If you remember the first term, this was in fact in the Laplace table. Let me just open it up. Okay, so if we have a transfer function with a denominator that looks like this, then taking the inverse of that will, so this is the denominator here, denominators here are exactly like what we have here. So that means when you take the inverse, you will have combination of these terms here, right? So depending on what you have on the numerator, you will have some combination of these two terms here. So which means you have an exponential function multiplied by oscillating terms. So if you okay, so in the general sense you will have something like this. So let's see what we have here. So these are oscillating terms. But all these terms are multiplied with an exponential function. So as opposed to what we had in the previous case, instead of having infinitely continuous oscillations, we have oscillations that are limited by this exponential function. So this should be a surprise, right? When we had a real pole, we had an exponential term. When we had purely imaginary poles, we had purely oscillating terms. And when we have both of them together, we have the two terms combined. Okay, and depending on the behavior of the exponential function, these oscillations can be growing or they can be decaying. And whether they grow or decay depends on the sign of the A term here. And just like the first case where we had real poles, if the A number is such that well, if it is positive, then minus A will give us a shrinking exponential term, and if A is a negative number, in which case that means the pole should be on the right hand side of the complex plane. In that case, the oscillation will be growing. Okay? Okay, now let's see what we get if we use the polar coordinates for expressing the pole locations. If we use the polar coordinates, then this is what we have. And the two poles are located at we call this difference omega n, and we call it theta, but we said cos theta is equal to zeta. So this part should be omega n times cosine theta, but cosine theta is zeta, and it's a negative number. And this part is omega n times sine theta. But instead of sine theta, I can express it in terms of the this zeta. So we have this trigonometric relation cos square theta plus sine square theta is equal to 1. But since cos theta is called zeta, this gives us that sine theta is equal to square root of 1 minus zeta squared. Okay, so this means the imaginary component of this complex number is omega n times 1 minus zeta squared within square root. Okay, so now the transfer function should look like that, subnomiated divided by s plus omega n zeta plus this quantity omega n times this thing. And now we have another pole. And for this pole, we have a negative number here for the shape interface, so there should be a j here, right? Okay, so open these two parentheses, and then that will give us s plus omega n zeta squared. Plus again this multiplies with the complex, the imaginary part here cancels, that multiplies with the other imaginary part, so I'm not writing that. I will have plus this multiplies with negative that, and that gives us omega n squared 1 plus zeta squared. Okay, and if I can do some calculations here. If I open this square term, this squared plus 2 omega n zeta plus omega n squared zeta squared plus omega n squared minus omega n squared zeta squared. So this cancels that, and then we get k divided by s squared plus 2 omega n zeta s, right? Omega n squared. Okay, so the summary of this is the following. If you are given a system with some numerical values, for example, if I tell you that I have a system with the following transfer function, s squared plus 2s plus 2, for example, and let that be true. So when you have that, you either make it look like this, and from there find A and B, or you compare it with this form, and from there you find omega n and zeta. Okay? In fact, let's do both of them and see what we get. 2 divided by, I should make it s squared plus 1 squared. So from here I will get s squared plus 2s plus 1. And I have plus 2 here, so that means I should have another 1 there, right? So which means my A is that would be confusing, I should write it like that. The poles are as -1 plus minus j. Okay, what we have, the omega square should be equal to 2. This gives us omega should be square root of 2. And 2 omega n times data should be equal to 2. But omega n is square root of 2. From here we get data is equal to 2 divided by 2 square root of 2, which is, ne yapıyor? Okay, so that is data. And if you plug in poles and complex, you see that they are consistent, right? So we have poles as -1 plus, so there is a pole there, there should be poles are here. And if you want to express using the omega n and data numbers, those are these numbers, square root of 2 and square root of 2 divided by 2. Okay? Let's see. Doğru. Kesinlikle. Yani if you have a third order system, then there are again several possibilities. One possibility is all 3 poles are real, and we talked about that before. Then you divide it into 3 first order systems and analyze it that way. Another possibility is you have a complex conjugate pair of poles, and the third one has to be real. In that case, you divide into 2 systems. One first order system with that real pole, and the second system will be a system like this. It will be a second order system with 2 complex conjugate pair poles. Nerede? Şuraya mı bakın? Şuraya mı olacaktır? Doğru. That's right, that has to be S. Okay, so the second order damped systems with poles at minus A plus minus BJ following terms in its response. Initial conditions.
Bunlardan yüzde yıkmaya yazarsak şöyle olacak değil mi?
Actually, the relation is obvious here. If you have, suppose there are two systems, okay, and suppose that these systems share the same imaginary parts but have different real parts. I'm talking about two systems as follows. I have one system and it has these poles, and the second system has poles here. So they both share the same imaginary part. They are both, let's call it B. But the first one has real part here, the second one has the real part which is farther to the left. And if you want to compare the response of these two systems, then by looking at here, they will have the same oscillating terms, but they will have different envelopes. Okay, so the decaying amplitudes of these oscillating terms will be decaying at different rates. And let's look at some examples on MATLAB. Okay, so this is the first case. These two poles cause a response as shown here. So this is the response initial conditions. You can see that from where the response starts. It starts from 1. The second case is this red one. So this is what I just showed earlier. They have the same imaginary parts, but the real parts have different numbers. So this means the frequency of oscillations are constant. So these parts are equal, but they oscillate within different envelopes. And if I add a third case to this one, which is farther to the left, then this is what you will have. And for me, we see that the frequency is the same because the peaks occur at the same time. So the peaks are all happening at the same time for all these three cases. And then similarly, they cross the real axis at the same points. So let's take a look at the next case. In the next case, we have, let's take a look at systems with poles that share the same real part, but the imaginary parts are different. So the first system is this one. The second system has poles here, and the third one has poles again with the same real part, but the imaginary parts are different. And if you look at the response here, this time we're keeping this thing the same, but changing the frequency. And this is what we have at the end. So things have different frequencies, but they have the same amplitude. So if you want to draw an envelope to these oscillations, it should be something like that, right? You can see that they all oscillate within the same envelope, but their frequencies are different. And we can see that from here. For example, let's take a look at the blue one. The blue one has the response, this response. The first peak was here. This is where it starts from. The next peak happens here. Okay, so this is at 2 pi. But if you look at the red curve has 2 cycles within 2 pi, right? So it has an intermediate peak point here, whereas the black one has 2 peak points in between. So these show that the frequencies of these responses are different, but they all oscillate within the same envelopes. Okay? Okay, so let's give a break and continue after that.